Hello everyone, thank you for attending. So as Juliana said, I'm currently in the second year of my master's degree that I'm doing at Institut Polytechnique de Paris. And here I will be presenting the work that I conducted during my 5 months internship at the I3S laboratory of Sophia Antipolis. And this part is more on the second part of my internship. And so I will be talking about automated reasoning on consistency models for replicated data systems with MONA. So here our main focus is on consistency models, where there are a few that are quite known, such as linear reusability, eventual consistency, reader rights, monotonic reads. So this is just a few examples. So linear reusability is about an operation being considered to be done at an atomic point in time. Eventual consistency is more about a convergence eventuality. Reader rights, each process always read a latest write, not the one before. Monotonic reads, once a process has read a value for data item, we cannot read an older value. So for instance, we have a few consistency models. But how can we ensure that a replicated data system respects such consistency models, for instance? Well, this gives a few problems. The first one, given an implementation of a replicated data system, can we formally and fully automatically verify that this system satisfies a certain consistency model? So this is on the replicated data system itself. So problem 2 is more when we have a distributed application that uses this kind of replicated data system. And we assume that it should conform to a certain consistency model. Can we formally and fully automatically verify that this application behaves correctly, so according of what we expect? So more generally, how can we formally and automatically reason about consistency models in replicated data systems? So two words that are quite redundant here are formally and automatically, and this is why we want to use the MONA tool that I will introduce later on. Just may I ask, who is familiar with MONA? Have you ever heard of the MONA tool? Okay, so to do. So the content and the outline. First I will explain the framework in which we are working, then how we perform consistency verification, and finally the conclusion. So, our replicated data system can generate a trace of execution. Here we call those traces histories. And we define a set HPTOE as the set of all those well-defined finite histories. And what we consider by well-defined is that P is a finite set of processes, which is quite important here. T is the type, so the type of operations we do. Here we only focus on read or write operations. O is the object, and the object is the replica of our data. And V is the finite set of value that can be either read or written. And a history is a set of operations, and each of operations has its attributes drawn from this set above. And we can visualize a simple history like this on two processes, for instance. And the dashed line represents when the process is idle, and otherwise the full segments represent an operation being run. So here I did not specify what A, B, C, D, E, or F are, but it's just an example. So we read our histories from left to right, naturally. But how do we link this with the MONA tool? But first I need to introduce what MONA is. So MONA allows us to perform automatic verification over logical formulas, in particular formulas from the weak monadic second order, so we call weak MSO or MSO. And it translates such MSO formulas into finite state automata. And just MSO logic is a logic that allows quantifications over object, sets, predicates. It has predicates, and it has also other restrictions that I will not mention here because we do not use them. But this is what we can do with MSO logic, more or less. And the automata's inputs are finite words of bit vectors. So MONA generates automatas, but those automatas need to have finite words of bit vectors, which are of this form. So this is 1 also, and we say bit because we only have zeros or 1. And these words are finite. So here the word finite is really important and redundant. And for the vocabulary, a vector is called a position, and a row a set of position. So for instance, this is considered a set of position, as this is a row across a few vectors. And so the MSO logic over such structures is more or less respecting this grammar. With quantification, we have comparison over integers because position and set of positions are numbers in MONA. And then we have the other formulas we all know. And so why we use MONA and MSO logic, why it seems so far away from our histories? Well, the major part of my internship was to prove this theorem, that the satisfiability of MSO formulas over finite histories is decidable. So I will not explain the proof here, because this is not the topic and it will be too long. So if you're interested, I can send you my paper with my internship report that contains the proof. But as here it's about MSO formulas over finite history, we look for a tool that handles MSO formulas, so for instance, MONA.
Is it true that general MSO is undecidable or something like that?
Here, well, I should have maybe written weak MSO formulas because it's over finite structures. But here what is important is that my proof is based on an algorithm that goes through all the operations of my history. So if my history is like infinite, basically the algorithm could not work. But my next point was to extending the result to infinite non-zero histories. Seems easy with a little, maybe with more weeks of my internship I could have proved it. But for instance, it was enough for the framework of the internship, so I did not dig further. But yes. So however, this implies that there exists an MSO logic of histories. Well, what is this logic? If A and B are some operations, we can compare their attributes. So here we have processes, types, objects, input and output value. And actually we can, of course, compare, I did not write it here, but the input value of A with the output value of B, for instance. We can compare the start and return time, quantification, as it is MSO, and sets also, and the other formula as well. We also need two supplementary relations that are not provided by the formulas of the grammar that I showed just before. So we consider that arbitration and visibility are given by some arbitrary algorithms that we do not possess. Let's say we just have these relations. We say that A is arbitrated before B if A is considered to be done before B. So this is kind of an omniscient point of view outside of the systems. We know that A is done before B, where A and B are some operations. Visibility is more that the effects of A, for instance, are considered to be visible to the process performing B. So this is more a point of view from inside the system itself. And those two relations will be quite useful to represent several consistency models. So on one hand side, we have MONA that represents a discrete time, so that can be seen as snapshots because we have vectors. While here histories are continuous, which can be seen as a timeline, and our goal will be to represent, for instance, for example, such a history from left to right as a sequence of vectors that can be read from left to right and represent what is going on in the history. So we have our traces of executions we call histories, and here we have MONA that looks for words of bit vectors as input. So that means we need to represent histories as words of bit vectors. So we need to perform the encoding. Then this is for histories, and for consistency models, we have MSO histories that I've introduced that we can link with histories. We have MSO words of bit vectors that we can link to histories as words of bit vectors. And so a second translation is needed, and if we have everything, well, we can perform our consistency verification. The translation between the two MSO I have been working on the compiler to do it, and I will not. I will just present a quick example at the end. But here we will mainly focus on this encoding function, because how do we represent histories on such vectors? Well, the vector structure is the following. I will do an example just after. So the first rows will encode what is going on the processes, then what is the type of the operation, its input or output value, the object, the arbitration relation, and the visibility. So I will go through an example explaining how we encode this. Let's take this quick example. Let's say we have process 1 and 2 with such operation. What we do is we mark when each operation starts or finishes. And here we need some information about A, B, and C, because we just have their names. Let's say we have yes, the colors are nice here, okay. Let's say their processes are indicated there, the start time, return time, the type of the operation, so write or read, the input value and the output value, and the object. So yes, we either have an input value or an output value, because we consider that when we write, we need as input the value to be written, and we return nothing, while when we read, we take as input nothing, and we will return the value that is read. However, we cannot use such values in our encoding, so let's say we have a function that is injective and provides us an encoding of those values. What we do now is that for each ti from t0 to t6, each ti will have its own vector. On t0, we have nothing to encode, no operation is being run, so no information to represent. Here, those dots represent the encoding that I will be explaining after for arbitration and visibility. On t1, we have A that starts being run. So the first row represents either an operation is being run on P1 and the second on P2. So we put 1 on P1 and we vertically encode the value in the table. So 1001, 1001. At T2, the operation stops. So we have zeros again. We repeat the operation for each T. T3, again, B is being run on P1, and we encode the attributes vertically. And here we have at T4 another configuration we have not met yet. It's when two operations are being run together at the same time, sorry. What we do is that we leave the one on the process of P1 and we just put information about C. And what we see here is that we encode information about the operation on only on the first vector that encodes it. Because this is enough, we need once to have the information about it. And this is how we manage to represent information about several operations being run concurrently. Then at T5 we have B that stops, so we put a 0. And as we encode no new operation, we put zeros elsewhere. And finally, at T6, we have that all operations are done. So this is mainly the main algorithm to encode the attributes of our operations. But now how we encode arbitration and visibility, because it is more tricky. For arbitration, we build an arbitration matrix. So here it will be, for example, here we have only at T4 that we have two operations being concurrently run. So here arbitration is interesting. Do we consider B to be done before C or C to be done before B? Well, here for example, we want to encode information in the matrix in this vector. And what we do is that at a given time, we consider does the operation being run on Pi is done before the operation run on Pj. And this is what I wrote in the sentence, that the variable alpha ij is set to 1 if the operation on process I is arbitrated before the operation on process j. So I have done a drawing because it's easier to understand. For example, let's say we have those three processes with those relations. So A is arbitrated before B, A is arbitrated before C, and C arbitrated before B. What we do is, do we have that, let's say, at a given time, it can be here to encode information about operation B. Does the operation on P1 is considered to be arbitrated before the operation on P2? Yes, because we have A arbitrated before B. So we put a 1. We reiterate P1, P3. We have that operation on P1 is arbitrated before operation on P3. We put a 1. And operation on P2 is done before operation on P3? No. It's P3 that is done before P2. So we put a 0. And the matrix is symmetric by reversing the values. So this should do something like this. So as it is symmetric, what is relevant are only those values. And this is those values that we encode vertically under the rest of the vector. So here we will have the previous encoding, and then afterwards we will have 1, 1, 0. And then the other encoding. Oh, yes.
Does it matter? I mean, you drew a vertical line. Does it matter when we consider this to happen? You understand my?
Yes. For example, it's not clear, but let's say that C starts after. So we have a vector each time a value, an operation, starts or finishes. So we have a vector here.
Yeah.
So here there will be no arbitration because A is the only operation being done. Here it starts being interesting because we have C and A. So here we will have...
Okay, it will be a 2x2 arbitration matrix at that point, maybe?
No, because it needs to be always about the same number of processes, but each time the value is not relevant to 0. And we can know that if you have 2, 1, 1 on the encoding, we know that we only have to look to certain values of the matrix. And visibility. A way to represent visibility with respect to a certain operation is to encode for each process the most recent operation initiated on this process that is visible to this operation. So I've done a drawing as well. For instance, we count operations from the end. So here we have respect to an operation A. So let's say that A is this operation. If we have that this operation is the most recent operation that is visible to A, we will count, so here that's number 1, number 2, number 3. We count from the operations being run before A ends, and we will encode the value 3 vertically here for process 2. If this is process 1 and this is process 2. So here it will, those values represent the binary encoding of the integer value we have here. And I've talked about the compiler quickly. It visually looks like this. The input will be MSO formatted with words. So for all capital X, there exists an X, there exists a Y, such that we have this formula. And the compiler that I've written outputs this, that can be executed in Mona. And so this is the syntax that Mona requires, and so this is how the translation is made between those two MSO. And it's ongoing work, so it's not completely done for the moment. And to conclude, we know that MSO satisfiability over finite histories is decidable, so this is the proof that I didn't show here. And we explain how we can formally and automatically reason about consistency models in replicated data systems, especially with Mona. However, as the internship was quite short, there is still some ongoing work. The compiler and some potential future work for the first part was to extend the proof to infinite histories. And then will be to weaken assumptions about visibility and arbitration, because for visibility, we considered that we use integer values, so we had a certain bound of the values we need to encode. So this is a restriction. And for arbitration, depending on from what I've read from the paper that I used to also work on this, it's only true we can encode only this if we consider the system to be real-time. So this is some restrictions we have. So thank you for your attention. If you have any questions, don't hesitate to ask. And that's it.
Thank you. Any questions?
Is the matrix supposed to be symmetric or
We take the values of the upper triangle part and we put the counter values. So it's not completely, it's not completely symmetric. It's the counter values. So if we have one, we have zeros.
but for one you counter it?
Sorry?
Okay, yes, okay, thank you.
So just to recap, so if I understood correctly, so you have if I give you a history, you can tell me if it's a model of a given MSO formula, right?
If we
Translate it first, and then you.
we translate, we use an algorithm to translate it into the encoding,
Yeah.
and we have formulas that represent consistency models in MONA.
Yeah.
And we run MONA on on the structure of the history with the given formula of the consistency model, and MONA tells us if it's satisfied.
If I give you a formula representing a consistency model, can you also answer some questions about the model itself using MONA?
Well, it will be on this specific history.
Okay, yeah, makes sense. Okay, well, let's thank the speaker again.